Hello, this is Math 125, Week 5, Lecture 2. Last time, remember, we defined equivalence relations and equivalence classes. Let us quickly recall the definition of equivalence class. First of all, what is an equivalence relation? Equivalence relation is a very special kind of relation, right? Which is reflexive, symmetric, and transitive. So if we have an equivalence relation, let's say S on a set S, right? On a set S, say on a set S, we have an equivalence relation. We have an equivalence relation, and usually we use this tilde symbol, right? So let us consider this tilde symbol, right? Let us denote the equivalence class with this symbol, right? So for each s, then for each s in S, the set, which set, remember, this is the symbol, right? This is the notation, right? Small s, right? And we put these brackets. So this denotes what? This denotes the equivalence class of the element s, right? So what is this set? By definition, this set consists of all t's in S such that right, S and T are related via the equivalence relation, right? We have on the set S. So this set is called the equivalence class, right? Equivalence class of small s. So the set is called this set. Of course, it's a subset of S, right? It's a subset of S, right? Equivalence class of little s is a subset of the set S, right? So this subset is called the equivalence class, right? The equivalence class of little s, right? Equivalence class of S or equivalence class containing S. There are different ways of saying this. Equivalence class of S or containing S, right? Or containing S. You can also say containing S, or equivalence class generated by S, right? Or generated by S. Generated by the element S. Right? You can call this in any way you like. They are all equivalent, right? They are all equivalent. Okay, so this is how we define equivalence class. Let me show you an example. Let us consider the congruence, right, relation on the set of integers. So for the congruence mod 5, right? Maybe 5 is big. Maybe I can consider just congruence relation modulo 3. Congruence relation modulo, let's say 3 on Z, right? So remember this tells us what is the relation, what is the congruence relation modulo 3. Two integers are related mod 3 if their difference, right, divisible by 3, or 3 divides the difference, right, of the numbers of the integers. So the equivalence class, let us write the equivalence classes for some elements, right? So for the congruence relation modulo 3 on Z, and the equivalence classes are the following. The equivalence classes of are as follows. Equivalence classes are as follows. Let us consider, for instance, 0, right? 0 is an integer. What is the equivalence class of 0? So notation, remember we introduced this. All the integers, right, equivalent to or related to 0 modulo 3 is denoted by this 0 bar, right? So this is the same as if you write this, right, in terms of this new notation, this is nothing but just the equivalence class of 0, right? Equivalence class of 0, integer 0. So what is this set, right? Which integers, right, are in the class of equivalence class of 0, right? So remember, the difference between the given integer and 0 must be divisible by 3. This is by definition of congruence relation modulo 3, right? So of course there are infinitely many of them, right? Let us start consider minus 6, for instance, right? So right, minus 6, the difference between minus 6 and 0 divisible by 3. Therefore, minus 6 is in the equivalence class of 0. The next number will be minus 3, right? Minus 3 and 0, their difference divisible by 3. And then, of course, 0 itself is in the equivalence class of 0, right? So, in other words, actually any element, right, will be in the equivalence class. We will show, actually, we will prove this later, all right? For any equivalence relation, take an element, right, of your set. Any element belongs to its equivalence class, all right? So 0 is in the equivalence class of 0, right, itself. And then next integer will be 3, of course. 3 minus 0 is 3, which is divisible by 3. And then 6, 9, 12, and so on, right? So this goes forever. Basically, you add 3 each time, right? You add 3 or subtract 3 each time. Okay, so this is the equivalence class of 0. What is the equivalence class of 1? With respect to this new notation, this is nothing but just bracket 1, right? Bracket 1 or 1 in the brackets, right? So of course this is more economical notation, right? More economical notation. So we usually use bar notation for congruence relations, right? Modular relations. So what are the elements of this equivalence class? So when we take a difference with 1, right, the number we get should be divisible by 3. So again, this goes, right, there are infinitely many such numbers, of course. So for instance, minus 4, right, minus 4, right, minus 4 is if you take a difference um, with 1, then we have it is divisible by 3, right? So minus 4, and then we have sorry, this is not true, of course. There should be 1 definitely, right? After 1 we should have 4 and 7, and when you subtract 3, of course, in the negative part, we have 1 minus 3 is minus 2, right? And then minus 2 minus 3 is minus 5, and so on, right? So this is the equivalence class, right? This is the equivalence class of 1 modulo 3, right? And it goes forever, right? You add each time 3, right? The next numbers will be here 10, right? 13, 16, and so on. And the previous number here minus 8, and then minus 11, and so on. You add 3, right, and subtract 3, right? So you get one can get all the numbers, right, in this way, in this equivalence class. Okay, and what is the equivalence class of 2 with respect to this notation, bracket notation? This is that, right? So this set consists of what? Let me first write 2. 2 is here, right? You add 3 each time. So 5, 8, and so on, right? You add 3, and you subtract 3 also, right? So when you subtract 3, minus 1, minus 4, and so on, right? Okay, so each of these classes have infinitely many, right, numbers, of course, right? Okay, so And remember, actually these are the elements of the set, right? Z mod 3 set, right? So Z mod 3 set. What was Z mod 3 set? This consists of the elements of Z mod 3 are these 0 bar, 1 bar, and 2 bar, right? Okay, so we saw this, remember. So actually what we observed here, indeed, the elements of this set, right, Z modulo 3 set, are nothing but just the equivalence classes, right, uh, um, right, of integers, right, modulo 3, right. So each element corresponds some equivalence class, right, equivalence class. Okay, so this is some basic example, right? Some first example for us. Okay, so but this example tells us what? So look, when you take the union of these sets, in other words, when you consider the elements, right? All the elements coming from all equivalence classes, right? Okay, if you consider all these numbers, we realize that actually we get the set of all integers, right? So, um, so this will be actually true in general. In other words, the set of equivalence classes actually uh, uh, this is some right. If you consider all the equivalence classes, if you put them together, right, the elements coming from all these equivalence classes uh, give us what? Give us the whole set Z, right? The whole set we have, right? So this will be true in general. We will actually prove this in this lecture, right? So let us observe the following important fact or facts. So, so this is some general statement. This is true for any equivalence relation. So let us, as usual, denote the equivalence relation with this symbol. Let tilde an equivalence relation on a set S, then we will have four statements. So for all, let's say S, T, U in S, we have what? The first part is the following. First of all, S is in the equivalence class of S. In other words, every element of the set S belongs to its equivalence class. Right? So this is the first statement. Second statement, the part B of the theorem, is if T and U are in the same equivalence class, okay, let's say we have some T and U which belongs to the same equivalence class, then they are related via the equivalence relation we have, right? So if two things belong to the same equivalence class, then they must be related, right? Via the equivalence relation we have, of course, right? Okay, and third statement is um, if the equivalence classes of two elements, let's say S and T, if they are the same, then this is if and only if, maybe I should write here, if and only if they are related. Okay, this is the third statement. And the last one, part D, either, right, for any ST in S, either the equivalence classes, their equivalence classes are the same, right, coincide, or uh, equivalence classes are disjoint, right? So given any two elements of the set S, right, given any ST from S, either those elements have the same equivalence class or their equivalence classes are disjoint. That means the intersection is empty set. Remember, by definition, equivalence class is a subset of the given set, right? So this is a subset of capital S, this is a subset of capital S. These subsets, they are either the same or disjoint, right? So This is part D. So let's prove this. Proof is actually very easy. Proof. So to prove A, all we need to observe actually the why A is true, because we have an equivalence relation. In particular, our relation is reflexive, right? So okay, given any S, right? Given any element S, why it belongs to its equivalence class? It belongs to its equivalence class because equivalence relations are reflexive. In other words, okay, you can prove this in the following way. Since tilde is an equivalence relation, okay, it is reflexive. It is reflexive. So this means S is related to S for all S in S, right? Right? But that means if S is related to S, look, if S is related to S for all S in S, that means any S belongs to its equivalence class, right? So S belongs to its equivalence class for all S in S. Right? So this is how you prove part A. Okay, part B is just the consequence of symmetry and transitivity property, right? So let us prove. So if T and U, if T and U, if T and U belongs um, to the same equivalence class, right? So we assume that if T and U in S, right, then they must be related, right? We want to show T is related to U via the equivalence relation, right? So if T and U in this equivalence class, in the same equivalence class, then by definition, right? By definition of equivalence class, T is related to S, right? T is related to S, and U is also related to S, right? T is related to S, and maybe I should try like this. If T and U is in S, then T is related to S, and U is related to S, right? U is related to S. U is related to S. Or S is related to U. Maybe using reflexivity, actually, you can change their orders if you wish, right? So U is related to S. Let me write it like this. So U is related to S, right? But since we have symmetry, right? If U is related to S, S is related to U, right? So this gives, right? Maybe I should write here. So this implies T is related to S, and S is related to U here by symmetry. Right? Since we have an equivalence relation, it is symmetric in particular, right? By symmetry. But this means now we can use transitivity, right? Equivalence relations are transitive. Therefore, if T is related to S, S is related to U, then T is related to U. So T is related to U by transitivity. Right, by transitivity. But T is related to U means what? T is related to U is just the thing that we want to prove, right? So this is also checked, right? This is also checked. So to prove part C, so we want to show if S and T have the same equivalence classes. This is if and only if S is related to T, right? With respect to the equivalence relation we have. Right? So this is what we want to show. So if so this is like if and only if statement, right? If and only if statement. So let us prove this part. So to prove this part means this direction means we assume equivalence class of S is the same as equivalence class of T, right? If equivalence class of S is the same as equivalence class of T by part A, then by part A. By part A, what we know, S is in the equivalence class of itself, and T is in equivalence class of itself. But we assume equivalence class of T is the same as equivalence class of S, right? Okay. So what we observe here, S is in S, T is in S is in equivalence class of S, T is also is in the equivalence class of S. Therefore, um, S and T must be related, right? Because right, so this tells us S is related to S. This tells us here T is related to S, right? So this is what we want to show. T is related to S. Remember, right? Assuming this, we want to show S and T are related. So this means T is related to S, right? So this is that direction. So for the other direction, right? For the other direction, this time we assume S and T are related, right? And we want to show they have the same equivalence class, right? So assume S and T are related, right? Okay, how can you show two sets? These are subsets, remember. How can you show two subsets are equal? If any element of, right, this one, right, any element of one of them should be element of the other, right? We need to show this. So let us start with by picking some element of the equivalence class of S, right? So assume we have this. Let um, X is in equivalence class of S. Then this means S is related to X, right? Thus, so this implies what? This implies um, um, T is related to X, right? So this implies T is related to X. T is related to X. This is actually here what we use here, since X is related to S, right? Since X is related to S, but we assume S is related to T, we use transitivity, right? Transitivity, by transitivity, right? But T is related to X means X is an element of equivalence class of T, right? By definition, right? So this implies X is an element of equivalence class of T. Similarly, right? Using the same argument, you can show that whenever we take an element of equivalence class of T, one can show it is also an element of equivalence class of S, right? Similarly, one can show, right, using the same argument, right? Right? If X is in the equivalence class of T, then it must be in the equivalence class of S, right? So therefore the equivalence class of S and T must be the same, right? So hence these three circles, remember, that means thus, hence, or therefore, right? Equivalence class of S is the same as equivalence class of T. Okay, so we proved part C. If two things have the same equivalence classes, this is if and only if they are related, right? They must be related to each other, right? Okay, so for the last part of this of the theorem, right, part D. So this tells us what? Either this happens or that happens. How we can show such statements? Assume one of them does not hold and prove the other. So for instance, let us assume there is an element, right? This intersection has an element. In other words, this intersection is non-empty. So assume this thing is non-empty. Right, non-empty. So then so say say there's an element, let's say X, right? Say X is in this intersection, right? This intersection is non-empty. Whenever intersection is non-empty, then one should show here, right? We need to verify that whenever they intersect non-trivially, they must be the same, right? Sets, right? Okay, this is what we want to show. Okay, then by okay, we proved part A and part B, right? By parts A and by part A and B, right? By these two parts. First of all, we have what? X is related to S, right? X is related to S. Look, we have an element in this intersection, so X is related to S and X is related to T, and X is related to T, right? So hence here using transitivity, S must be related to T. Of course, we also use symmetry here. So this implies, right, S must be related to T. If S is related to T, then we can apply part C now, right? So part C, right? If two things have the same, if they are related, right? If two elements are related, then they must have, this is if and only if, remember, they must have the same equivalence classes. So therefore, part C implies the equivalence class of S must be the same as equivalence class of T. Okay, so this is how you prove this very important, useful theorem. So this theorem is some fundamental, right, theorem. Fundamental means these properties, right, are true for any equivalence relation, right, so they are very useful in computations, right, or both in computations and both some theoretical arguments, right? So it's a very useful theorem, very useful properties. We will use them all the time, right? So this is some example and some important theorem, right? Stating important properties. Okay, so let me continue with a remark. Okay, remark. So part A of the above theorem, part A of the above theorem, actually implies the following. It implies that, actually it says that, right, or it states that every element of S, every element of S belongs to an equivalence class, belongs to some equivalence class, right? Belongs to some equivalence class, right? Remember, part A tells us what? Any little s given from the set capital S, right? Little s is an element of the equivalence class, right? Little s, right? Any element is belongs to its equivalence class, indeed, right? So that means what? That means when we take, right, thus we have the following nice, very important observation. The capital S is indeed, right, it can be obtained by taking the union of equivalence classes, right? Okay, so S, right, runs over all elements, right, of the capital S, right? For any element of capital S, consider the corresponding equivalence class, and these are subsets of capital S, right, by definition. So for any little s, right, consider its equivalence class and put them all together. Take the union of all these equivalence classes, right? And this union, since each of these equivalence classes are subsets of this capital S, right? And since we take the union over all, right, possible points, possible elements of the set S. So this union, of course, must be equal to S, right? Okay, so all of them, right, are subsets of capital S. Their union must be, of course, the set S, right? Because each of them are subsets of capital S, right? So this is a very important observation. Actually, this brings the idea of partition. We will define, okay, in this lecture very soon. Okay, so this is what part B actually implies, right? So also we have seen part D. Remember, part D. Part D implies that the same, of course, theorem, right? Right. Part D of the same theorem implies that any two equivalence classes, right? Consider two equivalence classes, right? They are either equal or disjoint, right? Are either, right? Let's say S and T, right? Little s, little t. The equivalence classes of little s and little t, they must be equal. Either they must be equal or disjoint, right? Either equal or disjoint. Right? This is the last part of the theorem, remember. Right? Thus, let us consider them together. Equivalence classes, their unions give the set S, but they are either the same, right, or disjoint. So this means what? This means S is the, right, if you have an equivalence relation on a set S, then S is the union of a set of disjoint, right, disjoint equivalence classes. Right? And this happens whenever we have an equivalence class on a given set S. Very general observation, right? So this suggests the following definition. So this suggests the following definition in some general definition. The following definition, or this suggests the definition of the following concept, which is actually what we call partition, right? So remember the title of this section, equivalence classes and partitions. Now it is time to define partitions of a given set, right? Partition of a given set. So definition, okay. Let S, this discussion, right? The definition of partition doesn't need any equivalence relation on the set, right? We are not assuming there is some equivalence relation. So you can define partition of a given set without assuming any equivalence relation on the set, right? So let S be a non-empty set. Non-empty set. Okay, non-empty set. By a partition, maybe I should state like this. A partition, okay, partition of S, right? Partition of S, partition of a set S, right, is a collection. Let's say any collection. It could be any collection, right? Let's say it's the set of some AIs, right? AIs should be subsets of S, right? So it's a collection of non-empty subsets of S, non-empty subsets of S, such that S dot T dot means such that, remember. We have two conditions. So such a collection is called a partition of the set S if the following two conditions are satisfied. First of all, we require that, remember the observation here, for if we have an equivalence relation, then this union of equivalence classes gives the set S, right? Union of all equivalence classes, of course. So the set S is the union of these AIs, and this I is some index, right? Index. Here we assume, since we have a collection, we have some indexing sets, right? It could be any indexing set, of course, right? So if we consider the union of all these, right, subsets, right? If we take the union of all the elements of this collection, and remember, member of the collection, this collection are just what? Any member is a subset of S, right? So if we take the union, that union should give S. This is the first condition. And the second condition, um, if we consider two, right, two elements of this collection, the intersection of any two elements of this collection, right? In other words, intersection of any two elements, any two subsets, which are the elements of this collection, right? Here, okay. This intersection is empty whenever the indices are different than each other. Whenever I is different than j, they don't intersect. Okay. Okay, so if I equals j, of course these are the same subsets, right? So this is very similar to that, similar to this property, right? Whenever we have two equivalence classes, either they are disjoint or they are the same, right? So actually, this is how we generalize this right observation to arbitrary, right, sets, right? And when we generalize, we give the generalization a special name. We say partition, right? Okay. So whenever we have this, whenever I is different than j, their intersection is empty, right? They are disjoint. That is, maybe I should write here. That is the subsets of the collection. The subsets of the collection are disjoint, right? The subsets of the collection, right? Subsets appearing in the collection, subsets of subsets in the collection, maybe I should say, subsets of S appearing in the collection, right? Right, this collection, right? This is a collection of subsets of S, remember. The subsets in this collection are pairwise disjoint, right? Pairwise disjoint. Here, pairwise means whenever we pick two of them, right? They must be they must be disjoint, right? This is the meaning of pairwise disjoint. Okay, so this is how we generalize, right, this observation for arbitrary sets, right? And we define this partition, the concept of partition, right, for a given set S. Okay, what is the important observation here? What is the important property of partitions? Okay, and what is the relation between right? What is how they are related, right? We defined partition here, right? But we also defined equivalence relation, right? And it seems that they have common properties, right? In other words, they are somehow related to each other. And the following theorem actually explain how they are related, right? Very, again, useful, very important, very fundamental theorem, right? This theorem has two parts. Part A, let tilde, right? As usual, let us consider some equivalence relation. Let tilde be an equivalence relation. Equivalence relation. Actually, the first part of the theorem summarizes the observation we made here in this remark, right? Let tilde be an equivalence relation on a set S. On a set S, all right? Then the set of equivalence classes, the set of, right, all equivalence classes, the set of all equivalence classes, equivalence classes of this equivalence relation, right? Equivalence classes of the set S, right? The set of all equivalence classes of S with respect to this equivalence relation form this set forms a partition, or right, the set of all equivalence classes, maybe I should say, I should write here collection of all equivalence classes, right? When we define partition, we use the word collection. Maybe I should say, I should also use collection here. The collection, right? The collection of all equivalence classes, right, of S forms a partition, forms a partition of S. Okay, so so equivalence classes, right? If you consider all equivalence classes together, that collection forms a partition for the set S, right? Whenever we have an equivalence relation, that means we have a partition for the set S, right? Okay. Okay, if we have an equivalence relation on a set S, then the set of equivalence classes, right, or the collection of equivalence classes forms a partition, right, or is a partition of S, right, basically. So part B, okay, so this is actually the other way around, right? So suppose we have a partition, right, okay, then can we construct some equivalence relation using a given partition, right? So part B answers that question, right? So if let's say we have some collection, right, AIs, right, some collection of involving subsets of some set S, right? Suppose this is a partition for the set S, or partition of S, right? So if we have this, then define the relation, define some relation on the set S as follows. Then define a relation R, let's say, on S as follows, by the rule, maybe I should say by the rule, or as follows. Okay, two elements of S, right? S and little t are assumed to be elements of this S here, set S. Two elements of S are related via the relation we have, right? We are defining the relation now, right? This is if and only if, right? This is the definition of relation R, right? S and T, right? This little s and little t, they belong to the same subset. They belong to the subset AI for some I, right? To the same AI for some I, of course, for some I, right? If we can find some I, some index I, so that S and T belong to the right subset AI corresponding to that I, right? Okay, if we have such AI, right? If S and T belong to some such subset AI, then we declare, we say that S and T are related via R relation. So this is the definition of relation R, right? Okay, so given a partition of the set S, we define this relation, right? And there is no claim, right, so far, right? What is the claim here? So theorem claims the following. This part of the theorem claims the following. The relation which is defined in this way is an equivalence relation. Then R is an equivalence relation on the set S, of course. Equivalence relation on S. Okay, so this is the theorem. Indeed, okay, you can also easily, right, observe, right, this equivalence relation. For this equivalence relation, what are the equivalence classes? Equivalence classes are just these AIs. Remember the definition of equivalence class, right? to right, an element, right, of the set S belongs to the equivalence class of T if S is related to T, right? This is the definition of equivalence class, right? Or T belongs to the equivalence class of S if T related to S via that relation, right? Equivalence relation, right? Okay, so here our equivalence relation is R, right? Theorem tells us such a relation is an equivalence relation, right? Therefore, from its construction, actually, we also know that equivalence classes, right, of equivalence classes of S with respect to this equivalence relation are just right these AIs, right? Okay, so this is how they are related, right? How partitions and equivalence relations are related to each other, right? So they are very strongly related. So proof, part A is already observed, right? Already observed, right? In the above proof, in the last proof, right? In the last remark, sorry. In the last remark above. Okay, so part A is done, right? Okay, part A tells us, remember, if we have an equivalence relation, then the collection of all equivalence classes of S forms a partition of S. Look here, what we observed, whenever we have an equivalence relation, first of all, the union of all equivalence classes, right, of that with respect to that equivalence relation, right, this union is the set S, right, the whole set S. So this is the first condition, right, in the definition of partition, right. And second condition, whenever right, we have two equivalence classes, right, whenever we have two subsets, they are if they are not the same, then they must be disjoint, right? But this is what we observed here, right? Equivalence classes, right? Equivalence classes, if they are not the same, remember there are two things, right? Two possible things. Either two equivalence classes are the same, are equal, or disjoint. This is exactly that condition here, right? So the collection of equivalence classes, right, of an equivalence relation on a set S forms a partition for that set or of that set, right? So part A is done. Part B. So to prove part B, what we assume here, we are assuming, right? We assume that there is some partition on S, right? So since AI, right, collection of AIs, right? Since this collection is a partition, right? This is what we assume, right? Since the collection is a partition, first of all, we know that S is the union of, right, these subsets AIs, right? Hence, look, any element of S must belong to some AI. So hence, any S in S, right, is an element of some AI, right? Right, some AI. Since this is a collection, since the set of AIs, right? This is a collection. This is a partition of our set S, right? This should be true by definition, right? Well, that means any S in S should be in some AI, right? Okay, should be in AI for some I, all right? So look, the relation is what? The relation S is related to T if and only if S and T belong to the same AI, right? Okay, so since S in for any S, that element for any S in S, there should be some AI here, right? So so S related to S is true for all S, right? Is true for all S in S. That is R is reflexive, i.e. R is reflexive. We are trying to show the equivalence relation R is an equivalence, the relation R defined in this way is an equivalence relation, right? This is what we want to show here, right? To prove B, we assume we have a partition, and we want to show the relation defined, given by this, right, condition is an equivalence relation, right? Okay, so this is a relation, of course, right? This is a relation. This is a subset of S cross S. No problem for that, right? It's a relation, but we want to show that relation is an equivalence relation. So we need to check reflexivity, right? And then symmetry and transitivity properties, right? So this argument, first of all, shows, right? Right? Why S related to S? Maybe I should say this. Why S is related to S? S and S belong to the same AI, right? Since S is in AI, of course, this condition is automatically satisfied. S and S belong to the same AI. There is only one element S here, right? And since we assume S is in AI, of course S is in AI. Therefore, this condition is automatically satisfied. Therefore, S related to S, right? This is true for all S in S. Therefore, this is just the reflexivity condition, right? So it is R is reflexive, in other words, right? R is reflexive, checked, right? Now we need to show R is also symmetric, right? If to see symmetry, maybe I'll say also if we need to start with two things, two elements, right? Okay, whenever S is related to T, then T must be also related to S, right? We want to show symmetric property, right? Symmetric property. So suppose S is in the same subset AI, right, as T, right? Maybe I should write. So if S is in the same, maybe I should write like this. Suppose S is related to T. Also, now suppose maybe I should say like this. Now suppose S related to T, sorry, R, right? We use R here. Notation is R. Suppose S related to T via R. So S is in the same, right, subset. S is in the same subset AI as T, but then that means what? S is in the same subset AI as T. So therefore T is in the same subset, right? AI as S, as S, right? Therefore, whenever S is related to T, T is related to S as well, right? So maybe I should write then this means T is in the same subset AI as S. So then this means T is in the same subset AI as S, but that means T is related to R. T is related to S, sorry, via R. So that is T is related to S. So whenever S is related to T, T is related to S. This is true for all ST, right? Whenever S is related to T, T must be related to S. So this is the symmetry property, right? So thus R is symmetric. R is symmetric. Finally, we need to show transitivity, right? We need to show R is transitive. Suppose now next, finally, suppose that, right? Suppose S and T are related and let's say T and U are related. That is, S and T are in the same subset, right? S and T are in, let's say, AI, right? For some I, right? And T and U, let's say they are in the same, they are in some other subset, let's say A sub J, for some J, for some J. But here T is in AI and AJ, right? So T is in AI, right? It is both in AI and AJ, therefore it is in the intersection, right? But so that means intersection is non-empty, right? So AI intersection AJ is non-empty. If look at the condition, we start with the, right, we assume that this collection is a partition, right? So if the intersection is non-empty, that means I must be equal to J. There is no way, right? There is no other way around, right? So either they are disjoint or they must be the same. This is the condition, right? Appearing in the definition of a partition, right? It's a condition for the collection AI. Therefore, right? Since T belongs to both AI and AJ, T is an element of this intersection. Therefore, this intersection is non-empty, right? So, but this implies I and J must be the same, right? Right? If I and J are different, then this intersection, right, cannot be non-empty, right? Okay, okay. So it must be empty. Right? This is the condition. Remember. So, so so this implies this means thus AI, right, right, thus AI must be AJ. In other words, I must be equal to J, right, right, okay, since the collection is a partition, right, as is a partition. Okay, so this shows us what? This shows us since AI and AJ are the same, in particular S and U, since AI and AJ are the same, in particular S and U are in the same subset, right? So S and U, right, are in the same subset, are in the same subset, in the same subset, right? But so does R is transitive, right? Right? That means S is related to U, right? S is related to U, right? S is related to U. So that means R is transitive. So transitivity also checked, right? Look, we check symmetry, reflexive, symmetric, and transitive, right? So the relation R defined in this way, we just observe that it's an equivalence relation, right? Equivalence relation. Okay, so let me show you some very quick examples, and then this will be all for today, right? So the first example is what's the very basic, the very first basic example of a partition. Again, we have seen these equivalence classes for congruence relation modulo 3, right? So the set of equivalence classes 0 bar, 1 bar, 2 bar, right? Okay, form a partition, right? These equivalence classes, remember, these are the classes of what? Of the equivalence relation, right? Congruence, right? Relation, right? Modulo 3 relation, mod 3 relation. Okay, equivalence classes of congruence, right? Congruence modulo 3 relation on, right? This is an equivalence relation, right? Equivalence relation. This is an equivalence relation, remember, on the set of integers z, right? So form a partition, right? These equivalence classes form or this set or the collection of the equivalence classes forms a partition partition of z, of the set of integers, right? And when we when we write these equivalence classes, we observe, remember, this is what we observed, the union of, right, these equivalence classes give the set of all integers, right? And each equivalence class, right, any two equivalence classes, right, or these equivalence classes are pairwise disjoint, right? If there is a number here in the equivalence class of 0, that number cannot appear in the other equivalence classes, right? So these are pairwise disjoint, right? Pairwise disjoint subsets of Z, indeed, right? So they satisfy the conditions of appearing in the definition of a partition. So these are partitions of Z, right? And this is true in general, right? In general, more generally, the set of equivalence classes 0 bar, 1 bar, 2 bar, and so on, up to n minus 1 bar. Here n is some right, natural number, let's say. Okay, natural number. Okay, the set of equivalence classes, right? This is the congruence relation modulo n, right? Okay, the set of equivalence classes, right? These 0 bar, 1 bar, 2 bar. So these are what? Modulo n, right? Equivalence classes of, with respect to, maybe I should say. Here, actually, equivalence classes with respect to congruence modulo 3 relation. Maybe I should say WRT. WRT means with respect to, remember. Okay, it's better to write with respect to here. Okay, the equivalence classes with respect to congruence relation, right? Congruence relation, congruence mod n, right? Modulo n relation. Congruence relation modulo n. Maybe it's better to write congruence relation modulo n, or congruence mod 3 relation. They are the same, but this is better to say, I guess. Congruence relation modulo n, right? Modulo n is some fixed, right? Fixed natural number, right? This set again forms a partition, right? Forms a partition of Z, of Z. Okay, this is some more general, right, example, of course. And finally, today I want to describe Q, right? The elements of Q as an equivalence class, as an equivalence classes with respect to certain equivalence relation. What was Q? Q is the rational number, right? The set of rationals, rational numbers. What is that? This is the set of all fractions of the following form. Let's say we have m over n. M and n are integers, so that n is different than 0, right? So m, n are integers and n is different than 0. So this is the set of all such fractions, right? So we call this set of rational numbers, right? So we want to, let us define the following relation. Define the following relation. Define a relation, and this will be some equivalence relation, right? Define a relation on Q. Relation on Q means it's a subset of Q cross Q, right? So how do you define as right such a subset? So M is related to N, right? Maybe I should write like this. Okay, sorry. Q is any element of Q is of the form M over N, right? So M over N is related to, right, P over Q. You want to define such a relation on, right, set of rational numbers, right? M over N related to P over Q, if and only if, right? Another way of writing this, right? Mn, right? The pair Mn is related to the pair PQ, right? Equivalently, we can also describe this as follows: Mn is related to PQ. Okay, you can also use this notation if you wish, right? Right. So two things, right? We want to declare, right? We want to declare. Maybe I should write like this: define equivalence relation. Okay, this is what you want to see actually. Sorry, maybe I should restart again. This is not true, of course. This will be the outcome actually. This will be the consequence of this construction, right? So look, this is an element of Q cross Q, right? This is an sorry. This pair denotes the rational number, right? M over N, let's say, right? This is such a pair is equivalent to some other pair, P comma Q, right? But the motivation is the following. Look, when right here, when M over N is the same as P over Q, right? So there are many fractions we have, right? Different fractions actually they are indeed the same, right? Ratios, right? So you can cancel common factors, and P over Q and M over N, they are the same, but maybe M and P, Q, they are different numbers, right? After canceling common factors, they are the same, right? We can see they are the same, right? So in other words, a given fraction can be expressed in many different ways. So we want to understand Q as a equivalence class, right, of certain equivalence relation. This is what we are trying to do, right? So here define the following relation on set of rational numbers as follows: M comma N related to P comma Q, right? So Mn and PQ are just considered to be rational numbers, right? So instead of writing M over N, we just write M comma N. Instead of writing P over Q, we just write P comma Q, right? So some notational, right, convention here. If and only if, right, this is how we define this relation. If and only if, look, two such ratios, when they are equal, if when we cross multiply, we get the same thing, right? In other words, if MQ equals NP, right? So this is how we define the relation. Look, this is what we want. MQ should be the same as NP. If this happens, then we say MN pair is related to PQ pair. Now, this is your exercise. Exercise, check that this relation is an equivalence relation. Of course, here N and Q are non-zeros, right? N and Q are non-zero. N and Q are non-zero. They must be non-zero, otherwise we cannot divide. Okay, we assume N and Q are non-zero integers, of course, right? So one can easily check This relation is an equivalence relation. Okay, equivalence relation. Sorry, this is not a relation on Q, of course. Equivalence classes will be ration numbers, right? So this define a relation on Z cross Z. Yeah. Okay, right? So this is an integer, this is an integer, this is an integer, this is an integer, right? Two pair of integers are equivalent, right? Are related if this happens. Okay, now it is correct approach, right? So show that this is an equivalence relation. So that means you need to show it is reflexive, symmetric, and transitive, right? Once we show this, remember our theorems, right? Once we have this, once you show this is an equivalence relation, what is the outcome? What is the consequence of this observation? Um, um, the equivalence classes, right? Clearly the equivalence classes, right? Each equivalence class clearly each equivalence class consists of infinitely many, right? Infinitely many ordered pairs, which we call fractions, right? Called fractions, right? Such ordered pairs are just fractions, right? Because m comma n, we just this is the notational convention, right? M comma n means m over n. P comma q is p over q, right? Called fractions, right? Called fractions, and then clearly we have this, and also observe that Q is just the right equivalence class of right. So this is the set of equivalence classes of set of equivalence classes of this relation. So for instance, 2 over 3, right? 2 over 3, this is just this is some rational number, but this rational number is indeed under this identification, right? Under this with respect to this equivalence relation, 2 over 3 is the equivalence class of 2 comma 3, the pair 2 comma 3, right? Look, 2 is like m, 3 is n, right? The equivalence class of the pair 2 3 is the fraction 2 over 3. It is what we actually know as the rational number 2 over 3, right? This rational number 2 over 3 can be considered as the equivalence class of the pair 2 comma 3 with respect to this right equivalence relation, right? Which is what we define here, right? So what is that equivalence class? So let's write some of the terms. Of course, 2 3 is here, right? 2 3 is here. 4 6 is also here. Why? Because when you multiply, look, 4 times 3, right? 4 times 3, right? This is n times q, right? N times q is equal to 6 times 2, right? 6 times 2, right? So 2 3 and 4 6, they are related, therefore they must be in the same equivalence class. Remember the theorem, right? We proved. Also, another term, for instance, could be this: minus 10, minus 15. Let's check these two, for instance, why these are in the same equivalence class. There are infinitely many of them, right? We cannot list all of them, of course, right? In each equivalence class, there are infinitely many terms. We cannot list them all, right? But what are the property they must satisfy here? So when you multiply, right, m and q, this is our m, this is our q, right? So 4 times minus 15, it is minus 60. it should be the same as n times q. N is here 6, q is minus 10. So 6 times minus 10 minus 60. Minus 60 equals minus 60. Therefore, these two pairs, right, they belong to the same equivalence class with respect to this equivalence relation, right? So what is 2 comma 3? 2 comma 3 is actually 2 over 3, right? What is 4 over 6? 4 comma 6 under this identification, right? Right? 4 comma 6 is just the fractions 4 over 6, right? This is 2 over 3. This is 4 over 6. What is that fraction? This fraction minus 10 over minus 15. Of course, right? Of course, all these numbers are, we know that they are all equal, right? Right? After canceling common factors, right? Right? Cancel 2's, you get 2 over 3. Here, cancel minus 5, right? Minus 5's, you have again 2 over 3, of course, right? So this is how we can describe the set of rational numbers as the set of equivalence classes of certain equivalence relation. This was a little bit longer lecture, but I guess okay, still okay. Okay, so this is all for this lecture. See you later. Bye.